So our last speaker for this mini symposium is Antonio Girao from Heidelberg University, and he will talk about subgraphs of large chromatic number and connectivity.
Right. Okay, so first of all, I'd like to thank Stefan and Felix for inviting me, and I have to thank as well Owen, without whose help this would have not been possible. So thanks, Owen, as well. Right. Okay, so the problem I want to talk about today is related, so it has to do with the following. So suppose you are given a graph of a high chromatic number. So how can you guarantee, or is it always possible to guarantee, there exists a subgraph which has both high chromatic number and high connectivity? Right. Even this qualitative statement is not clear. But let me say a few words. So it's well known that high chromatic number implies subgraph. There exists a subgraph with high average degree or minimum degree, which in turn, by a result of Mather from 72, implies there exists a subgraph of high connectivity. Okay, I should have said, we say that
Antonio, sorry, if you write a little bit bigger, I think it'll be better.
Yeah. Right. So a graph is k-connected if any pair of vertices, one needs to remove at least k vertices to disconnect. Okay, so high chromatic number, you have a subgraph of high average degree, and high average degree, you can find a subgraph of high connectivity, and actually the loss is always linear, so you only lose a constant factor. And here, the problem could be is that this subgraph could be bipartite. Sorry. Right. Okay, so suppose now that I want to guarantee that this graph also has high chromatic number. Okay, so that's the question. And so let me give a brief overview of what was known. Probably it is better if I go down. Right, so the history is, so the first people considering this problem were Allen, Lightman, Thomason, Sachs, and Seymour in 1987. Okay, and they showed it, the qualitative statement. So for every k, there exists an f of k such that chromatic number greater than f of k implies there exists a subgraph which has number at least k and connectivity it's at least k. Okay, now their bound was f of k cubic in k, so big O k cubed, and they asked whether this could be decreased. Right, so more recently, Chudnovsky and Scott and Trotimon 2013 were able to reduce the bound to quadratic. Okay, and right. Okay, so now obviously there's a question where this f of k is the right answer, or if it could be decreased. But we just started thinking about this problem because of the recent breakthroughs on the Hadwiger's conjecture. So let me give a brief overview of that. So Hadwiger's conjecture, everyone knows that. So it states (44 or 45) So for every t, chromatic number of a graph is at least t, or strictly greater than t minus 1, it implies there exists a kt minor. Right, so the first, it's not hard to show exponential in t, just a nice induction argument. And then the first breakthrough was by Stoch and Thomason in 1984, and they showed Stoch and independently Thomason. So they showed that, so they actually looked at a slightly different problem. They actually found the correct average degree to guarantee a kt minor. So if the average degree of a graph is at least big O t times square root log t, then there's a kt minor. Right. Okay, so since, and this is like 84, and since then, nothing better than this average degree barrier was known until very recently, where Norin, Song, and later Postel, but now actually the paper is together. Okay. Norin, Song, and Postel were actually able to show. So the first bound breaking this average degree barrier. So they showed log beta t for O beta greater than a quarter, and then more recently, Postel showed a bound of t times log t some power. Right, and in between these two theorems, which wasn't that long, like 1 year difference, like 2019, it's beginning 20. Norin asked whether it would be quite nice to know to make this reduction. So if I'm given a graph with chromatic number 100k, it would be quite convenient for their method, which I don't know. But he asked whether you could reduce the problem to start with a graph which has both high chromatic number and high connectivity. Obviously, you are not trying to aim for the Hadwiger's conjecture, but if you are trying to just go for, say, a linear, so for a constant factor away, then perhaps if this function f here, if we could decrease it to linear, it could be helpful, and that's what we thought, and that's exactly what Postel used. So I think our result was instrumental. Of course, his result is by far much more complicated than just using our result, but in particular, our result was used by him. Okay, so let me state the theorem. Right. Okay, so we prove that so 7k is enough, and okay, few remarks. Allen, Kleitman, Thomason, Sachs, and Seymour have proved that a lower bound of 2 here, and I think our methods would probably be able to, definitely would be able to reduce this 7 to 5 or even 4, but not to 2, so we didn't really. Okay, but it's almost tied up to a constant. Okay, so let me give, okay, I stated the theorem, so now let me go for a sketch of the proof. And let's see how basically the proof is finding a nice setup. And once you have the nice setup, it's actually not hard. Okay, so suppose, okay, so this is first just intuition. or how we started thinking. Okay, so you are given a graph with, say, chromatic number 100K, right? How can we construct this subgraph, which is highly connected? And so it seems intuitive that a minimal subgraph with this property should somehow have quite nice connectivity properties. So the intuition is, okay, so given G, and chromatic number of G, say 100K, take subgraph minimal with this property. Okay, and then, okay, so suppose, so we know G prime is has high chromatic number. Now suppose it doesn't have high connectivity. Okay, so we can find two sets and delete a set R. R is at most K, and there's no edge between. Okay, then we could say, but now look at here. Okay, this is strictly smaller, so we can find the coloring using at most 100K colors. So coloring C delta, say. And now, of course, and now you have to put these, so when you look at this graph, you have to put these pre-coloring somehow interacting with the coloring there. Okay, and so this gives rise to the definition of a pre. So you must allow some set of pre-colored vertices, and some guys here also have some set of forbidden colors, because if they are adjacent to some pre-colored guy of color 1, say, you can't give color 1 there. Right, okay. So it seems that the approach is to actually have a more general definition of coloring. Okay, and then for that we define we define something called a template. Okay, so now I just need to give 2 or 3 definitions. I think the hard part is the definitions, the rest are. Okay, so the definition. Okay, first I'm going to assume C is the palette of colors throughout. Okay, and size of C, I'm going to assume is 7K. I just number them. Okay, so now as a definition, we say T, which is a triple CSF. This is just, I mean, I'm perhaps being too formal, but it's clear what it will be. Is a template. If, okay, S is a subset of the vertex set. C is just a pre-coloring from S to C, and then F is just a function that for every vertex associates a set of forbidden colors. Okay, so that's a template. Some vertices, most of the vertices which actually be f of x equals the empty set, so you allow all possible colors, but some vertices you have to restrict the number of colors you can color there. Some vertices actually color. Right, okay, so we have the definition of a template, and now we need the definition of how to extend a template. So T is extensible, and now it's the obvious definition. So T is extensible if there exists a proper coloring. Sorry, I should have said G, let's say our graph G is fixed. G is fixed. So the palette of colors is fixed, G is fixed, and the template in G is that. And T is extensible if there is a proper coloring C. Or C might not be good, so let's say C star from G to the palette, such that, okay, C star of X equals C of X for all X in S. So this respects the pre-coloring. The C of X is not in F of X, or in other words, C of X is in C except F of X. Okay, and for all vertices, the C star is in C. Okay, so a template is extensible if the pre-colored vertices are given the same color. So if you have a proper coloring, which pre-color are given the same color, forbidden, and each vertex is not in its forbidden state. Right, okay. And finally, we need to define, like, obviously there are templates which are not extensible, because if you, for instance, put the f of x, the entire palette of colors, obviously you cannot find the color inside C except f of x. So we need to control what are the nice templates, okay? And in order to control, so we need to define a function on the templates, which we call the norm, just such that it has some kind of additivity properties. Okay. And so we define, so the norm of a template equals, remember, template is always a triple, so C is F, so just K times, so every pre-colored vertex we give weight K, and then for every vertex we just give the weight, which is the size of its forbidden set. And obviously, so what we want to say is that the norm of the templates we want to consider is not too large. So you don't have too many pre-colored vertices, and or the sum of the forbidden sets is not too large. Okay, but with these definitions, I claim we are almost done. Okay, so now sketch of the proof. Okay, so let G be a graph with chromatic number greater than 7. Okay, so in particular, there exists a template which is good. I'll tell you what is good in a bit, for which G, that template cannot be extensible in G. Okay, so now, so given a graph with chromatic number 7k, let G prime be a subgraph of G, minimal with the following property. So the property is that there exists a template T such that, so one, okay, the norm of T is not too large, and two, f of x is at most an upper bound, so the set of forbidden causes is not too large as well for every x. Right, okay? Okay, so G is minimal with property that there exists a template satisfying these two things, and T is not extensible. Of course, extensible in G prime. Okay, so it's a minimal subgraph, if you want to induce subgraph, with the property that there exists a template which doesn't have high norm, and the set of forbidden, the size of the forbidden sets is not too large, but yet you cannot extend. Okay? Okay, and now we are done, in a sense, because that is the candidate. So we claim, so now we just need to prove that G prime has both high chromatic number and high connectivity. Okay, so claim chromatic number, sorry. Yeah. I shouldn't have, I changed the order of the things. Okay. Anyway, perhaps I can put this up. This stuff. Okay. So chromatic number is at least K, and connectivity of G prime is at least K. Okay, so to prove that the chromatic number is at least K is not half. So you have to work a bit more in this case. So let's see roughly what is the idea. Okay. So let's say case 1. So we are going proof of 2. Okay. So suppose not. Okay. So then we have two sets V1 and V2 and the set R. R is at most K, such that there are no edges. So if it not means that it's not K connected. If it's not K connected, means we can delete a small set that we have two non-empty sets. There's no edge in between, or it's small. But if it's small, it's clear that it's extensible. So we can assume it's large. Okay. So suppose not. Then we have this. Okay. So a nice property. So the property of the norm is that when I restrict the template to a subset of the vertex set, which is, okay, I don't want to be too formal, but it's just the set of pre-colored vertices intersection with this vertex set, the functions restricted to this vertex set, and so on and so forth. So the norm of that plus the norm of T V1 union R is equal to the norm of T. Okay, so this in particular implies that either norm of T restricted to V1 is at most K squared, or the norm of T restricted to V2 is at most K squared. Okay. This norm is increasing, so going to smaller set of vertices can only decrease the norm. Okay, so then we have, okay, let's assume is this holds. So, okay, then let's define here, this is S intersection V1. Remember, S is the set of, S is pre-colored vertices. Right? So this is the intersection. Okay, remember, the norm is, if everyone can see, is K times the size of the set of pre-colored vertices. So in particular, because we know the norm is at most K squared, in T restricted to V1 in particular, we know that the norm of this is at most K. So we have at most K pre-colored guys here. Okay, so the first trick is that we look at part, okay, and we add all colors here to the set of forbidden. So we add all colors here to all sets of forbidden colors for every vertex in R. Okay, so suppose this guy has color 1. Okay, so we add 1 to all forbidden. If the 1 was there in T, in the template T, okay, we do nothing. If not, add it. Okay, then simple calculation every time. So this guy doesn't belong to this template. So you are deleting from the norm of T, you are deleting K every time because this guy is not considered. And you are having at most one guy for every such set, but R is at most K. So you delete K, add K. So in particular, so let's call this new template T, and this is a template on V2 union R, which is the same as T restricted to V1 union R, except that the forbidden you add those colors. So then the norm of that is at most the norm of T, because these guys do not appear, and for every guy you delete K and add at most K. Okay, and then this implies by minimality that there exists a C star. C tilde, which extends YT, okay, tilde is at most the norm of T, so in particular satisfies 1. And okay, I didn't say, because it could happen that the forbidden guys, when adding this set of forbidden colors, you increase these too much, but you can assume that the template T doesn't have a too large set. So in no vertex, actually you can assume that in T, f of x is at most k, because otherwise you can just pre-color it and you decrease the norm. But this is a technicality. So in particular, T tilde satisfies those two properties. The graph is strictly smaller, so by minimality it must be extensible. So there exists a color which extends T tilde. Okay, and now what we do is, okay, now let's look at this graph. And we know that T, remember T restricted to V1 have norm at most k squared. And we said that at some point here. And so, and now I add those set of R to the set of pre-colored guys. And I'm adding at most, there's at most k guys, so the pre-coloring on these R guys is just the pre-coloring, is just the coloring of C tilde on R. Okay, but I'm adding at most. So this new template, which let's call T star, is at most the norm of T in V1 plus k guys here. Okay, so each one contributes with k squared. Okay, but this is at most 2k squared. And this satisfies again both properties. This is strictly smaller, so it's extensible. Contradiction, because then the entire, we have a proper coloring of the entire graph, which extends the template T. Because in particular, okay, I didn't say, but in particular, C star extends the restriction of the template here and the same thing. Okay, and to prove the chromatic number is basically the same sort of argument. Yeah,
Antonio?
I don't know how are we in time, but that's about it.
Cool. Perfect. Okay, so let's first thank Antonio for his talk.
I have to go closer.
Is there any question? I think we have time for a quick question and then we should wrap up. So this result of Postel, there's also a list coloring version, right? Is this also using your?
We also have a list version. Actually, it's even, interestingly, it's even easier to prove the list version of this.
I mean, your proof looks like a bit like a list.
Yeah, but I cannot say that his list version actually uses our list version. I don't know.
Mm-hmm. Any other question? Okay, if not, then let's thank Antonio and all the speakers again, and thank you all for coming. I hope you enjoyed this mini symposium and learned something. I definitely learned a lot of new stuff. So